All right. So here we will refer to our tutorial. So in this case, what has been learned so far? Just to recap, to revisit a little bit, in the last class, last week, we already covered on how the mathematical model can be derived according to the mass and energy conservation principle. So once we obtain this model, what are we going to do? Of course, this model represents the given case study. So in order to represent the given case study, we need to solve the model. We need to interpret it qualitatively. So how we are going to do that, then that means we need to put the number inside the mathematical model and see how this model is behave, either is increase or decrease. So this is the topic for today class. We obtain the model, then we want to solve the model in order to represent the given case study. So here I use the past test question to illustrate on how the model can be developed, and from the model how it can be solved to represent the given case study. For this case, I used two liquid storage system as shown in the figure 1, and each tank is having a 3 feet in the diameter. So we assume this both tank has a liquid storage, and has a similar diameter. Alright, so based on this, the mathematical model is not given. Now, before we go to that question, now we want to interpret what is the difference between these two case study. So let's name it. So this one is the, let's say the first one, case 1, and this one is the case number 2. So this tank has the inlet flow rate Qi. So here if we refer to the question, the inlet flow rate has the unit of feet cube over minute. So this means the flow rate is based on the volumetric flow rate. So the Q given here, Qi and Q is represent the volumetric flow rate. So in this case, the unit is the feet cube over minute. And then in this case, the difference between these two liquid storage system are lie in the exit flow rate. You can see in this case, for the case number 1, we have this item. And for the case number 2, there are additional items located in the exit flow rate. So for this case, this represents different equipment located at the exit flow rate, where the case 1, the symbol here represent the pump. And the second case study represent the valve. So in this case, first, we need to have the process understanding. How the process is behaved qualitatively. So without having the number, having the value, we need to visualize what happened to our liquid system. Now, if we take a look, you have the Qi coming into the system for both storage system, and then you have the exit flow rate. So in this case, that means the main variable that will be changed will be your volume. So volume inside the storage system will be changed because here you have one inlet and the one outlet. Depending on the value of your inlet flow rate or the outlet flow rate, the volume inside will be changed accordingly. So this volume can be extended to represent the level, where here you can see the variable used is the H. So H, sometimes we refer it as the height of the liquid inside the tank, or sometimes we simply call it as a level. So in this case, there are two additional equipment installed at the exit flow rate, which are the pump and the valve. So normally for the pump and the valve, both has different function. Where normally the pump, we will have a continuous flow rate. Or sometimes we have a fixed flow rate. So the function of the pump, normally we will set what is the desired flow rate for this stream, for this outlet. Let's say you want to make sure you have 10 kilogram per hour. So the pump will make sure it will flow 10 kilogram per hour continuously. That is the function of the pump, to make sure the liquid is transported from one point to another point at the fixed flow rate. So this is the function of the pump. Meanwhile, for the valve, normally the term used will be regulating flow rate. So the function of the valve in this case, it will regulate flow rate accordingly. Regulates means this value of the flow rate is subjective, can be increased, can be decreased. What factor deciding this increment or decrement is based on the level inside of the tank. So when it depends the level inside of the tank, that means there will be a specific relationship to represent the change. Normally for the valve, we will use Q equal to H over R. So where this one, what we call it, linear relationship. This linear relationship is the standard form for the valve. So whenever you encounter with the valve, then we will use the linear relationship, where the linear relationship consists of the Q equal to H over R. So where the H here is your level, and the R here will be your resistance for the valve. And normally the resistance of the valve is a constant value. So whenever we have the use of the pump or the valve inside the storage tank, that means different mathematical model can be obtained. So how it is differ? Let's take a look. We start with the case number 1. In the case of the pump. Case 1 with the pump. So based on this, we will start with the overall mass balance. So in the overall mass balance, in this case, we start with the dm over dt equal to mass in minus mass out. So where here we can relate the m with the density multiplied by volume. So you get d rho v over dt equal to m in. The mass flow rate coming in, so you have the Q. So the Q given in this case is the volumetric. So since you want to have a mass, that means you need to multiply it with the density. So for this case, the rho I multiply with the Qi minus rho multiply with the Q. Where here, Qi represent your inlet and the Q will represent your outlet. So there were only one inlet and one outlet involved for this storage system. Then, based on this, we can further expand our equation. Rho dv dt plus v d rho over dt equal to Q. So based on the previous assumption, the density will not be changed against time, so that one can be neglected. And also we assume the rho equal to rho in equal to constant value. So when you have the constant value, that means your equation will further reduce. We can eliminate the presence of density inside the equation, so that leaves you the equation become dv over dt equal to qi minus q. So we have the overall mass balance for the given system. So if we refer back to the diagram, the figure, in this case you can see the volume is represented by the level. So that's why you have the H inside your tank. So when you have the H indicate as a height or the level, then that means the overall mass balance in the form of volume needs to be extended to represent the level. So in this case, we know that the V equal to area multiplied by height to represent the volume inside the tank. So we substitute the equation. And then we have the A dH dt plus H dA over dt equal to Qi minus Q. So according to this, you have two terms on the left hand side, where the first term involves the A multiplied with the dH over dt, the change of the height against time. And the second term is the H dA over dt, the change of the area against time. Since we normally use the fixed tank, the same shape tank throughout the process, that means the cross-sectional area for the tank will not be changed against time. So it remains constant. That means you can neglect the dA over dt. So this end up with the A dH over dt equal to Qi minus Q. So this is the final overall mass balance for the given case study. Any questions so far?
Sir, does the pump adds energy to the system? Q.
Okay. So in this case, do we consider the energy from the pump? Alright. Now what we are interested in is the balance. So normally in this case, as we know before, we have three types of the balance. The overall mass, component, and the energy. So based on this, do we need all of the balance? So we need to put into perspective. This unit operation involved is the liquid storage system. So normally the function of the storage system is to store the liquid. It's just a storage. So that means normally the component is not needed for the storage system. Because in the storage is just the function is just to store your liquid. So that means there is no federation, no blending system and so on. So you don't need the component. And in addition to that, the storage system normally store at the ambient temperature. So when you have the ambient temperature, then you don't need the energy balance. So what you need is only the mass. So meaning that in this case, if you have the energy from the pump, we can neglect it. It's not considered. Because here you don't have any temperature change. Let's say your inlet is hot, then we just let it cool down naturally. So you don't need to do the energy balance. The one that we are interested in is the overall mass balance because it will change your level. Any other question? Just to add, sometime in the final examination or the test, normally we don't ask you to derive all of the balance. So you need to read the question, what is the balance needed to solve the problem? And then you need to analyze, understand the given figure, for example, to find what is the relevant variable. In this case, it's just locate Qi, H, Q. No T, no X. So that means you don't need to concentrate on the energy and the component balance. The only balance matters in this case will be the overall mass. Alright, let's continue. So we have the overall mass balance A dH dt Qi minus Q. So this one has been covered before, how to develop the mathematical model. So in this case, what we are interested in is to solve the model accordingly. So in the case study 1, by using the pump. So you have the A dH over dt equal to Qi minus Q. Alright. So based on this mathematical model, we will cover the step on solving the given mathematical model. So there are so many ways, so many approaches to solve the mathematical model. What we are interested in is to use the Laplace transform. We adopt the Laplace approach to solve the differential equation given. So before we go to that, we do the next. The first step in solving is the development of deviation variable. So this is the step after you obtain the mathematical model. So in the deviation variable represent the equation dynamic state minus the steady state, where the ds is the dynamic state and the ss will be your steady state. So in this case, the mathematical model that we obtained before, A dH dt equal to Qi minus Q, represent the dynamic state of our equation. So this is the dynamic state equation. Or sometimes I call it as a ds, as a short form. ds represent the dynamic state. So you have the A dH dt Qi minus Q. So the deviation variable is the difference between dynamic minus the steady state. So how to obtain the steady state equation is just we follow the same mathematical model. A dH over dt equal to Qi minus Q. In this case, normally to differentiate equation between the dynamic and the steady state, we adjust or we include this different symbol for our variable. For example, in this case, we know that the level is going to change. And this part, we have the H equal to H bar. So you can see here, you have the H bar. So H bar in this case represent your dynamic state, steady state. What is mean by steady state? So this means normally the steady state referring to the initial value. The value at time equal to 0. So this means the H is going to change. Whenever it's changed, that means it must have the starting value. This starting value represent the value at time equal to 0 before the process start. So that's why you put it as a bar. The same goes with the Qi. Qi, you have the bar to indicate the Qi will be changed. Here it does not mention either your inlet flow rate is constant or not. So we assume it is a variable. The variable that will be changed in terms of its value. And then in this case, how about A? Do we need to put the bar in A? A represents the cross-sectional area. So my question is, do we need to include the bar inside the A? Why? May you provide why you don't need to include?
We use same tank. Area does not change.
Okay, thank you. Here the A is the cross-sectional area. Normally the area is based on the shape. The shape is not going to change against time. So this represents the constant value. A is the constant value. So when you have the constant value, you don't need to put the initial condition because the value is not going to change. H, the level is going to change. That's why you put the initial condition as H bar. For the A, you don't need to do that because it's a constant value. So this indicates when you have the variable as a constant value, then the variable remain the same. You don't need to put the bar to indicate it as the initial value. How about Q? How about Q?
Need.
Why do we need to put the bar?
Tak perlu kot.
If it's not necessary, why? You need, normally in this case, if you provide yes or no, you need to back up, support your answer with the justification.
Because
No.
pump is fixed flow rate.
Again,
Because case 1 is pump and the pump is for fixed flow rate, so it doesn't change.
yeah, correctly. If we refer back to the definition of this pump and the valve, pump is based on the continuous flow rate, or sometimes we call it the fixed flow rate. So fixed flow rate means the flow rate remain constant when you use the pump. Like I said before, I want to make sure the stream has 10 kilogram per hour. So I put the pump. So pump will flow in 10 kilogram per hour continuously. So that means the value is not going to change. So this is the thing that you need to take notes. Whenever you have the pump, the outlet from the pump will remain constant. So when you remain constant, that means you don't need to put the bar. So it remains as it is. So this is what we call it deviation variable equation. Deviation form or deviation variable. Where based on this, this is what we call it steady state condition. So this represents the steady state condition of your equation. Or sometimes we call it as the S.S, steady state. So according to the deviation variable, the dynamic state will minus with the steady state value. So normally we just subtract term by term, where in this case, normally the A will form in the form of this. So we just follow the same form. We start with the A is remain there, and then since A multiply with the differential equation, then the deviation form will be dH minus H bar over dt equal to Qi minus Qi bar. So we subtract term by term. And lastly, minus Q minus Q. So this is the way how to form the deviation variable, where we subtract the deviation, the dynamic state minus the steady state condition. So based on this, we can further classify where the equation A dH prime over dt equal to Qi prime. Where in this case, what is mean by H prime? H prime normally is the deviation form. H prime equal to H minus H bar. And the Qi prime equal to Qi minus Qi bar. Dynamic minus steady state. So this is what we call it deviation variable. So how about the Q? Since the Q here if we take a look on this term, the Q is the constant value. So the value is not going to change. So that means you don't have the bar or the prime over there. So the Q minus Q simply 0 because you subtract the same variable at the same value. So that's why in this case, you only have A dH prime over dt equal to Qi prime in the derivation form. Alright. So, based on this, we can see that the equation is going to be changed. Normally, based on the overall mass balance, what you get is okay, it's normal. You have the A dH dt equal to Qi minus Q. But when we use the pump, according to the derivation variable, the Q will be remain constant. So that leaves us the A dH prime dt equal to Qi prime. So this is the mass balance in the form of the derivation. Any questions so far? Okay, if there is no question, then we continue. So we have the equation of the derivation form. A dH prime over dt equal to Qi prime. So the next step to solve the model is to do the Laplace transform. So in the Laplace transform, if you have the textbook, you can refer. In this my case, I use third edition. Third edition, you refer to the Laplace transform in the appendix. If you refer to the third edition, the Laplace transform that we are going to refer is in the appendix A. Table A1. Refer to the table A1. So in this case, if we refer to the table A1, you can find the equation number 24. 24, this indicate that if you have the equation ft df over dt, then the Laplace transform fs will become sfs minus f0. Okay, so this is the thing that we are going to do. Based on the appendix A, table A1 in the textbook, third edition, process dynamic and control, whenever you have the differential equation, whenever you have this form, then when we try to do the Laplace, you will follow the following form. That is the standard one. So it's just not that you need to do it manually. You can adopt what has been done, what has been Laplace by the previous work. So we just adopt the form of the Laplace transform. So if we try to reflect it in our model, so whenever we have a df over dt, you get sfs minus f0. We can see the f here has been changed to the capital F, and then you put the bracket of the s to indicate it is under Laplace transform. So in my case, imagine that if I change f to h prime, what happened? So I put dh prime over dt. So when I do the Laplace, I follow the same form. The Laplace transform based on the differential equation start with the s. So I follow the s, and then here you can see the f small letter has been transformed into the capital letter. So I just follow the same form, h prime, and then I put the s. Why the small letter has been changed to the capital letter? Normally to indicate it has been Laplace, just to differentiate. Why I put the prime? Because f you don't have the prime, because here I just follow the form. Here I imagine the f is my h prime now. So I replace h prime with the f. That's why for the Laplace I have the s, h prime s, and then I have minus, you have the f, small letter, so I put h prime 0. So this indicate how you can do the Laplace transform for the given differential equation. So whatever we have the differential equation, we just follow the same thing. dh prime over dt is become the s h prime s minus h prime 0. So this is the Laplace transform for the given differential equation. Any question regarding the Laplace transform?
No question, sir.
Alright. So now if we take a look, you have the a dh prime over dt. We just focus on the left hand side first, how to do the Laplace transform, and for this case you have the a dh prime over dt. You have a here. A is your constant value. So normally when you have the constant value, we just simply put a here, a dh prime dt. So you multiply with the a here. It's like that. Because a is the constant. So constant value, when you do the Laplace, still you get the same form. So you don't need to worry about that. So for this part, the left hand side, when I do the Laplace a dh prime dt, then it become a s h prime s minus h prime 0. Just to put into perspective, this one a dh prime over dt equal to qi prime. So this is normal function, and the bottom one is the Laplace transform. A dh prime over dt, when we do the Laplace, it becomes a sh prime s minus h prime 0. So how about the qi? The qi here is just the variable. So whenever you have the Qi, you do the Laplace, then you just have the following form. Qi prime S. It's just the same form, only the difference is you change from the small letter of Q to be capital letter of Q. And then you put the S bracket to indicate it is under Laplace. So that's how you can do the Laplace transform for the deviation variable. Only the difference, in this case, if we can see, differential equation, little bit different. You have to follow the form. If only variable involved, then you just change from the small letter to the capital letter. And then you indicate or you include the S bracket for showing it has been Laplace. So, based on the A dH prime over dt equal to Qi prime, we already do the Laplace transform. So, where here, this is the Laplace transform equation. So, what is the next step? So, once we have this, then we can do the further step involved, which is to simplify the equation. So if we take a look, we have the A and then we have the bracket S multiply with the H prime S minus H prime 0 equal to Qi prime S. So what is mean by the H prime 0? So here the 0 indicate the time. The time. So it refer to the steady state. How about the H prime? If we take a look on the deviation variable, this is our H prime. H prime equal to H minus H bar. What has been developed in the deviation form. H prime represent the H minus H bar. So this indicate if we have H prime is equal to H minus H bar. So if we have H prime 0, then that means H0 minus H bar 0. So this means if we follow it consistently, although we have the in bracket 0, so we need to follow the same form as we developed for the deviation. So if we take a look by definition, H prime 0 equal to H0 minus H bar 0. So this means both variables refer the same value at time equal to 0. So meaning that the H prime 0 here can be considered as the 0. Do you agree?
No.
Why?
Maybe there's a initial height.
Okay, thank you. Alright, in this case, why I put H0 minus H bar 0 equal to 0? So we take a look on the definition. What is meant by the H0? So the H0 is the level at time 0. And what is meant by the H bar 0? level. H bar means that also refer to the level at time 0. So meaning that the H0 and the H bar 0 refer to the same state. When it's referred to the same state, of course, because here we involve the same variable, the level. So the trajectory is similar. The starting point must be similar. So that's why, whatever the value of your level, in the end you get 0. For example, here the level at time 0 is 4. Here, let's say, H equal to 4. Of course, level at time 0 for the H bar must be H equal to 4. The same variable. So that's why in this case, the H prime 0 equal to 0. Because the state referring at the time equal to 0. In other words, the H and the H bar 0 referring to the same starting point. So this represents the same state and then you can neglect it. So what happens next is this part will become 0. So we reduce or we simplified the equation. So this means our equation now become A S H prime S equal to QI prime S. We don't have any H prime anymore. So we have a S, H prime, and the QI prime S. So here we can see that the A is your cross-sectional area, the S, small letter of the S is your Laplace, the H prime represent your level, and the QI is your flow rate. So normally in this case, the level is also known as your control variable. Hence, it is also identified as your output. And your flow rate, since you have the QI, I represent the inlet. So here it is your inlet flow rate. So in this case, the next step after we do the Laplace is to obtain what we call it transfer function. Where the transfer function definition is equal to output over input. So what is mean by the output over input? So here refer to the variable involved, variable identified as your product or the outcome. And the input represent what is your feed. In this case, the feed referring to the inlet flow rate. So based on this, the transfer function, if we try to rearrange it, the H prime S over QI prime S equal to 1 over AS. So this is what we call it transfer function equation. Output over input. This part has a long step, involve multiple steps. Take your time to digest it. So that's why in here I think you already you can notice why there are so many failure in this subject. Imagine that if you have a wrong mathematical model, then it will affecting all of it. And we are not halfway yet.
Sir,
Ya.
yang level tu kenapa dia jadi output ya?
Yang mana? Level.
Uh-uh.
Okay. Normally when we have this one, if we take a look, your equation like this. Case 1, pump A dH dt equal to Qi minus Q. So based on this, is represent the overall mass balance. The mass itself can be related with the volume. The volume can be related with the level. So what we want to observe here is our level. We put the in and the out and see what is the outcome of our level. Increasing or decreasing. Thus, by observing this variable classified as your output. It's not input. And in addition to that, normally the dH over dt. Lastly, we want to observe the level. Of course, when we want to observe the level, this is our outcome. Then it become our output lah. This output means what do you want to observe in the end? What variable that you want to observe? So this considered as your output variable.
Okay, sir.
Okay, I think we take a break. Just take your time to digest the information. We continue around 5 minutes later. Okay, all right. So it's already 1:07 p.m. So we continue the lesson about the transfer function. So here what I show in this Microsoft Word in this document is the way, is the guideline how to solve step-by-step procedure. By deriving the mathematical model, then we develop the division form. Then it's followed by the Laplace transform. Once you obtain the Laplace transform, then we obtain the transfer function. So the next step involving the what we call it inverse Laplace. Inverse Laplace. So the inverse Laplace means we convert Laplace into time domain. Into the time domain. So here we have the Laplace form, which is what you can see. You have the H prime S. So S is the Laplace form. So based on this, we want to convert the H prime S into Q into H prime T. From S Laplace into T. T is your time domain. So when we have the H prime T, that means the equation is ready to be solved. So in order to make sure it can be solved, now we refer to the question. Suppose that initial state of both systems are h bar 14 feet and qi. So here the h bar, the original feet, original level, the initial level will be 14. And the qi is 7 feet cube per minute. And then after 5 minutes, the inlet flow rate. Okay, the inlet flow rate suddenly changed from 7 feet cube to 5 feet cube per minute. So this is the information given to you by this question. So what we want to observe, we can see that here we have the qi prime. Based on the deviation variable, we have the qi prime equal to qi minus qi bar. So according to this qi, your inlet is 7 feet cube and then it's changed to the 5. So we can substitute the value inside our derivation form, where now 5 minus 7, you get negative 2. So this is what we call it derivation value. How the value is going to change. According to this, what we can observe is why we need to develop derivation form. The derivation form represents how the process can be changed, how the variable can be changed. So that is the reason why the derivation step will be included during the solving of your equation. So we use the derivation form to get the magnitude negative 2. So this is the change of the qi. Negative 2 means the value has been decreased by magnitude of negative 2. You decrease the value by 2. So here we want to make sure we have the h prime, it can be changed into the h prime t. So this indicates that your equation here, if we try to rearrange it, H prime S equal to 1 over AS multiply with the QI prime S. So in this case, based on the derivation form, you have the small letter QI prime, where the small letter here represent the negative 2. So based on this, if we try to catch your input is like this. So this is your QI versus time. Initially is the value of your inlet flow rate at 7. Now it has been decreased by 2. So this is 7 and this is 5. Where the magnitude is negative 2 equal to M. M is the magnitude of change. So the profile normally is like this. When you change the value, you get the sketch of your input based on the decrement or increment. So for this case, normally this is what we know as a step change. You can see the change is like a stair. Either it's increase or decrease, it's like a stair. So this is what we call it a step change. So in this case, we have the QI prime equal to negative 2. Based on your equation, you have the QI. So meaning that the QI here cannot be straight away to substitute inside the equation. You need to do the Laplace transform before you can do the substitution. Again, let me write it again. H prime S equal to 1 over AS multiply with the QI prime S. So now we know that the QI prime equal to 2, negative 2. So this is based on the step change. If we do the Laplace based on the step change, you can refer to table A1. Table A1, number 2, unit step. Where whenever you have the ST, the Laplace transform will be converted into 1 over S. This is the default value. So since the step change here, negative 2, then when we try to do the Laplace, the QI prime, when we want to convert into QI prime S, negative 2 here will be converted into negative 2 over S. Or if we try to imagine negative 2 multiply with the 1 over S. Where here the Q is not the constant value, it's the variable, it's changed from 7 to 5. So it's changed based on the step. When you have the step, we have the Laplace transform of 1 over S. So we just multiply the magnitude with the 1 over S. In this case, the magnitude of change is negative 2 over S. And then you have, we can substitute negative 2 over S inside our equation since it has been Laplace. So you have the H prime S equal to 1 over AS multiply with the negative 2 over S. So we already complete the substitution of the inlet flow rate. So now here the problem is the area. We don't know the value of the area. So since this involve the water, the liquid storage system, then normally the area is based on the cylinder shape, where A equal to pi multiply with the r square if you use the radius, or pi d square over 4 if we have the information in the form of diameter. So you can use either one depending on your information. So here the diameter has been given. If we refer back to the question, is this indicate that each tank has a 3 feet in diameter? So we have the information of the diameter. So in this case, based on this, we substitute the value of pi multiply with the 3 over square over 4. So you can calculate the value of your area. Please calculate it for me.
9/4 pi.
Again.
9/4 pi.
Can you put it into the number? Multiply with the pi.
7.0685.
Feet square. So this is your area for the storage tank, 7.0685. So normally for test or final exam, you need to make sure you have a consistent decimal point. If you use 4 decimal point, then you use 7.0685. Or maybe if you want to use 2 decimal point, then it should be 7.07 feet square. For standardization, at least maintain at least 2 decimal point for your answer. Do not round it off, become 7. Then you will be wrong. So the acceptable between 2 decimal point up to 4 decimal point. So let's say in this case I use 4 decimal point. So your answer should be 7.0685. Now H prime S equal to 1 over AS 1 over 7.0685 S multiply with the negative 2 over S. So in this case, H prime S, please divide negative 2 over 7.0685. Anybody? Negative 2 divided by 7.0685.
Negative 0.2829, sir.
2829 over S square. Anybody else get the same answer?
That
Yes.
Alright.
Same.
Okay. So now we already substitute all of the transfer function, all the value, for the each variable. So we want to do the inverse Laplace. So if we refer to table A1, table A1, number 3. So whenever you have the Ft, T, and then the Fs, 1 over S square. Alright. So according to this, if I have the Laplace transform of 1 over S square, then the time domain will become T, small letter of T, where the T here referring to the time. So when I want to do the inverse Laplace, in this case, the H prime S become H prime T automatically, equal to negative 0.2829, because I have S1 over S square, then it become T. So this is my inverse Laplace. So we need to, I repeat it again. Now I have this form after substitution. H prime S equal to negative 0.2829 over S square. So where in this case, I want to convert the H prime S into H prime T. And then here, I notice that based on the table A1, if I have 1 over S square, then it become T. So my equation negative 0.2829 over S square. So this one, if I do the inverse Laplace, it's like this. 2829 1 over S square, where the negative 0.2829 is my constant value. And I have 1 over S square. So I just substitute 1 over S square with the T. So in the end, for the inverse Laplace equation, I obtain H prime T equal to negative 0.2829 multiplied with the time. Alright, so I got my inverse Laplace equation. So it can be solved now. So our objective, if you take a look, in the beginning, I have this form. A dH prime over dt equal to Qi. So my objective is to solve this problem, to obtain the value of the H. So I follow the Laplace transform approach for this given case study. So if we take a look on the question again, in this case, suppose the initial state of our system are H bar 14 feet and Qi bar 7 feet cube per minute. After 5 minutes, the inlet flow rate has been changed from 7 to 5. Predict which tank will empty first. So this is the question asked by the test. Predict which tank will empty first. Empty after long period of operation. Alright. So we have the H prime over T. Now case 1, pump. We H prime equal to 0.2829. T. Alright. So now we know that the H prime here represent the H minus H bar equal to negative 0.2829 T. Now we know that the H bar is 14 and the question asks you to predict which tank will empty first. Empty means no level. The solution has been exiting the system. So no liquid is left inside the tank. So this contribute to the H now is 0. So that's why for the H minus H bar, H is 0. Minus H bar is the 14. Equal to negative 0.2829 T. So in this case, we already substitute the value so we can determine the time. How long it will take for the tank to empty from the 14 to 0. How long it will take. So based on this, find what is the value of the time.
49.
49. 49 point?
0.4875.
48. 48749 lah. Minute. So this is the time needed for the tank to become empty. So if we try to reflect in our graph, at time 0, H. So this is your current level, 14. Now this one becomes 0. So how long it becomes 0? So this is the time 49.49. It will take around 50 minutes for the liquid to become empty. So this is the answer for the case 1 with the pump. So this means when we use the pump, it takes around 50 minutes to become empty. So if we take a look on the question asks you predict which tank will become empty first. So you need to compare the tank with the valve and the tank with the pump. So now we already complete the case 1 pump. So before we go to the case 1 with the valve, case 2 with the valve, any question?
No question, doctor.
Alright, so we continue with the case study 2. So still we have the time, now it's 1:31. So now I want to solve case number 2 because here the question asks you to predict tank 1 or tank 2. Case 1 or case 2 will become empty first. So we have the same level, 14 feet. How long it will take for the valve or the pump to ensure you have empty, it become empty. So for the case study 2, with the valve, it has the same inlet and the same outlet. Case 2 with the valve. So since it has the same inlet and the outlet, so that means your overall mass balance should be the same like what you have with the pump. So the overall mass balance should have the following form. A dH dt equal to Qi minus Q. So this is the overall mass balance for the valve. Only in this case, the valve has the following relationship Q equal to H over R, where this is the standard relationship for the valve. Whenever you have the valve, you can use this standard linear relationship. Alright. So whenever we have this relationship, then that means we need to substitute into our equation. So this become A dH dt equal to Qi minus H over R. So once we substitute the relationship, what is the next step? So we follow the same procedure, where the first procedure is to obtain the derivation form. So in the derivation form, this is your dynamic state equation. Now we want to obtain our steady state equation, where for the steady state equation, A dH bar over dt equal to Qi bar minus H bar over R. If we take a look, in this case, the A, you don't have any bar because it is constant. The H, of course, the level will be changed. The inlet, of course, will be changed. And then here, the R. R is the valve resistance. Normally, the valve resistance has a constant value. So you don't need to include the bar. So this become your steady state equation. Now in the derivation form, the dynamic minus the steady state, your equation become A dH prime over dt equal to Qi prime minus H prime over R, where in this case we know that the H prime equal to H minus H bar, the derivation between the dynamic minus the steady state, and the Qi prime equal to Qi minus Qi bar. So once we obtain it, the derivation form, we need to do the Laplace transform. This one, we still follow the same procedure. Here, I just move a little bit. The detail can be referred to the previous Laplace transform, how you can do the Laplace. So here, when we want to do the Laplace, our equation become A S H prime S minus H prime 0 as H prime S minus H prime 0 equal to Qi prime S minus H prime S over R. So you can take a look on the left hand side, you have the differential equation A dH prime over dt. So we just take the form to become A as H prime S minus H prime 0. Meanwhile, for the right hand side, the Qi become the small letter q become capital letter. And then you put the S bracket to indicate it has been Laplace. And for the H over R, it's become the capital letter H prime S over R. So in this case, we know that the H prime 0 can be neglected as a 0. So that leave us the A as H prime S equal to Qi prime S minus H prime S over R. So in this case, you can see on the left hand side you have the H, and on the right hand side you have the H. So this refers to the same value. Then we can factorize the equation. So you can get ES H prime S plus H prime S over R equal to Qi prime S. So we obtain the following equation. Now we factorize the H prime S AS plus 1 over R equal to Qi prime S. So we already factorized the level, then the next step is to obtain the transfer function, where the transfer function based on the definition is output over input. So this leads to the H prime S over Qi prime S equal to 1 over AS plus 1 over R. So this is your transfer function, where you get H prime over Qi. Only here the difference is the form. Before this, on the case of the pump, your transfer function only obtain this one, H prime over Qi equal to 1 over AS, only single term, 1 over AS. Now it's a little bit complicated, where in this case you have H prime over Qi prime equal to 1 over AS plus 1 over R. So we obtain the transfer function, and the next step is we want to do the inverse Laplace. So in this case, we want to make sure we from H prime S we convert into H prime T. So in this case, we know that the Qi is the same thing. Qi prime is equal to Qi minus Qi bar. It's the same thing. The same input has been used. Of course, for the sake of comparison, similar input must be used. Then we can have the fair comparison. So for this part, still you get 5 minus 7 equal to negative 2. The same like what we did for the case of pump. If we have the Laplace transform, then this one become negative 2 over S. It's like that. So in this case, if we try to rearrange it, H prime S equal to negative 2 over S multiply with the 1 over AS plus 1 over R. So we can see this one almost there. Now we can substitute the value. In this case, the same shape of the area. So the area before is 7.0685. Area equal to 7.0685 feet square. So now the value of resistance. Value of resistance is not given. It's not given in this case. So let's assume. Assume R equal to 2. So this is, I just put the assumption. R equal to 2 in order to solve the model. So let's substitute the value. So H prime S equal to negative 2 over S. Multiply with the 1 ES 7.0685 plus 0.5. So this is the substitution of the value. Now I want to convert my equation into the inverse Laplace transform into the time domain. If I take a look on the table, there is not much transformation. So this, if we refer to the chapter 4, if you refer to the page 61 under table chapter 4, section 4.2, page 61. Alright. So chapter 4, section 4.2, page 61. So here we refer to the equation 4.17. Equation 4.17. In this equation, it stated that when we have the ys equal to km, s tau s plus 1. Then the inverse Laplace should be yt equal to km 1 minus exponent negative t over tau. So this is the standard inverse Laplace when you have km s over tau s plus 1. So we reflect our equation back. H prime S equal to negative 2. Negative 2 over S 7.0685 S plus 0.5. So this is our equation. Negative 2 over S, okay. So we have like this. So right now I want to convert H prime become H prime T. The problem here, you can see the form is little bit similar. You have the S here. You have the S here. The km. can be represented by the 2. Tau maybe 0.0685. You have the S. Only the problem in this case, the bottom part here is plus 1. Mine is 0.5. So in order to have a similar form of the given YS, I need to convert. I need to convert 0.5 to become 1. So here what I can do is negative 2 I take it outside 0.5 as 7.0685 s over 0.5 plus 1. So now by taking out the 0.5 outside the bracket, then I can have plus 1. So in this case, h prime s equal to, what is the value of negative 2 divided by 0.5?
Negative 4.
Negative 4 over 7.0685 divided by 0.5. 7.0685 divided by 0.5.
14.1372.
14.1372.
1372.
Let's say 14. S plus 1. So now I have the same form like I have for the YS. So if we compare it, this equation with this. So I know that my Km equal to negative 4. My tau equal to 14.14. So by having this, that means I can use the following inverse Laplace. So yt become h prime t equal to Km negative 4 and then 1 minus exponent negative t over 14.14. So I already able to do the inverse Laplace. So we just use whatever we have for the form. So in this case, ys km over s tau s plus 1. If you have this form, then you have the standard inverse Laplace. However, my question, my transfer function has the plus 0.5. So I convert it become 1 to have the same form as we have for the equation 4.17. So according to this, I already convert become plus 1. I have the same symbol. Then I can directly use my inverse Laplace. So I change the Km with negative 4, the tau 14.14. So this is what I get, where the h prime here is h minus h bar equal to negative 4. 1 minus exponent negative t over 14.14. It's like that. So this is how you can solve the problem. Now we already done the hard part, so you can continue with the easy part, which is answering the question. Where the question here state, predict which tank will empty first after long period of the operation. So we already finished the pump, where the pump taken around T49.49. And this one, please solve it by yourself and you can check the answer with me later on. So this is the topic for today. I know it's a long way. So you need to time to digest it. Please study back the given exercise, the given tutorial, follow the same step, repeat the step to familiarize on how to solve it. So this is the only beginning. We will see this kind of problem later on. And you will expect the test question will exactly like this. So it's around 1:53 now. I think we already exceed the given time. So let's have a quick question from any of you.
Doctor,
Yeah.
for to find the t, right, I get math error for the equation.
Math error for the question.
Yeah.
Okay. Thank you. Thank you for your participation. Try to solve the problem. All right. Now, in this case, one of your friend get the answer. T become math error. How come the T become math error? All right. This is the thing that I want you to explore further. Why you get math error? It's supposed to be you get T equal to certain value. Why? I keep the answer for now. Maybe I would like you to think it first, discuss with your friend, and maybe later on I will share the answer in the WhatsApp group. I will share some simple video maybe by Friday on why you get negative or other answer. I let you to discuss with your friend first. Okay, any last question before we finish? Okay, if not, then I strongly recommend for you to do this exercise again, and I'm open to discussion. If you have difficulty later on, please consult with me. You can reach me through my WhatsApp number. Then I can assist you in the best way for helping you understand this topic. So with that, thank you again for your attention. Thank you very much for your cooperation. I see you online next Monday. Okay,
Thank you,
thank you.
Doctor.
Class is
Thank you,
dismissed.
doctor.
Thank you, 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 Doctor.